And we also did, I think I put the equation for the solenoid down, right? Field, or the actual formula for the solenoid. At least that's what I have in my notes. Is that right? Here's, maybe the class before. This is where we, remember we started with the loop, single loop, we got the H field from it, and then we took a cylinder. All right. So the solenoid is just a cylinder with a whole lot of turns of wire. And we ended up getting that, right? I'm gonna do one other, well, I wanna give you one other configuration that's common, that it's called a toroid. Does anybody know what a toroid is? Just take that long solenoid and twist it into a donut. That's a toroid. Now this is something you encounter all the time. What it amounts to is you're gonna have basically something like this. Think of a donut, a circular cross-section wrapped with a whole bunch of wire. And just go ahead and keep extending that as it wraps all the way around. And I'm not even gonna put them around, but you see all the way around here. So we have n turns, right? And then we're gonna have what's called the mean radius, A, and that goes to the center of this donut. I mean, not the center. It's really, it's halfway between the beginning and the end of the thickness of the donut, if that makes sense. Now, this donut is gonna have a cross-sectional area that looks like this, and the diameter would be D, and what they normally do is give this a value, something different than A. I'll call it R here, and RC for core. So now what they would like to do is find the H field in the center of this toroid. That seems reasonable, right? We're gonna make a few assumptions, and it's almost always, not always, but most of the time done this way. First thing we're gonna say is that RC is much less than A. So in other words, this radius here is much larger than that. That's the first thing. Then after we make that assumption, I can say that the cross-sectional area here, this cross-sectional area, A, would be either pi RC squared, or it could be pi D squared over 4. And that would mean that you simply replace R, instead of RC, you would have D over 2, you squared, you get D squared over 4. Everybody agree with this, class? Now, once you have that, then the next thing you're gonna do is use Ampere's law. And the integral of H dot dl around a closed loop is really the I enclosed by the loop. And here's where you're gonna have to you're gonna have to be careful about this. So if I make my Amperian loop right through the center, all the way around, that's gonna show up. I was looking for a different color, but it won't work. In other words, if I have this as my path, that I'm gonna take the H field on. Some of this is hard to envision. You see, if you have, anytime you have wires, coils of wire, like this, if I just have a bunch of coils of wire, oh, let me do this. There's a thing that they might have taught you in physics. If you assume that there's a lot of turns, and this is a long piece of metal, or a core, then if you want to know the direction of the H field in that core, you find the direction of the current in the wire. So I'm going to assume I circulating that way. Take your right hand and use the fingers of your right hand to grab the actual current in the direction it's going. Follow me? Can everybody see that? And your thumb points in the direction of the H field. The H field will be going this way. Now, if you do that same thought process here, if we've got current circulating this way, say, if I is going this way, doesn't really matter which direction. If you take your fingers in some ways and grab that, and then your fingers have to point in the direction of the current, your thumb points in the direction of the H field. And you're gonna see that the H field inside there, it could vary a little, all right? And we'll give you that. If we're here, it's gonna be a little bit stronger than here. But anyway, when we take the integral of H dot dl, really what I'm gonna do is take the integral where rho is gonna be somewhere here I'm gonna make this, rho is gonna be greater than A minus RC and less than A plus RC. In other words, I'm gonna assume that I'm between here and here. I'm where the H field is. Follow me, class? And now I say that the integral of H dot dl would just be really the length of this path times the H field. And that would be, the length of that path would be 2 pi rho times H phi, and that would be equal to I enclosed. Now, how much I is enclosed? Well, think about if you took that coil, this is a reduced size copper, bless you, and you just cut it in half. Well, if you cut it in half, where's my eraser? Oh, thank you. If you cut it in half, then you get this. You basically would get this. You would have this. That makes sense to you. I'm just trying to help you view this. Well, current is coming out. If it's circulating this way, the windings are that way, it's coming out of that, going in here, out of that, in here, if you follow me, right? But how much current is actually inside this loop? Take a look at that. How much? If there's I in one current, how much total current is encased there? N times I, right? Does everybody see that? Because I'm trying to find all the current that penetrates the loop, really the area of the loop, so that would be N times I. And therefore, H phi inside there is really Ni over 2 pi in the A phi direction. Now that's how you get that using Ampere's law. It's an easy thing to do. I'm going to say one thing. Usually this is assumed about, 2 pi rho. Usually this, and this is for rho greater than, or I should say rho inside, just put inside. Inside core. And that's all you need to know. But this is an application of Ampere's law, and it makes it really easy. Now think if you had to do this with the Biot-Savart law, and you had to take a differential amount of current, find the differential H field at a point, and then integrate that over the entire loop. It's doable. It's a tricky integral. I think it's an elliptic integral. But it would still be a lot harder than doing it this way. That's how come exploiting symmetry and knowing how to use Ampere's law is so valuable. Everybody agree on that? Now, I'm going to just tell you, that's what the H field is for a solenoid. If you wanted it for, for a toroid, if you wanted it for a solenoid, I'll contrast this. I put this, I know I did this, and this is going to be length L, and this is radius A. And if I want the H field right here in the center, H in the center of that, H here would be equal to Ni over 2 pi, over 2 times the length L. And then it has these integrals of Z plus L over 2 over the square root of Z plus L over 2 squared plus A squared plus, Z minus L over 2 over the square root of Z plus L over 2 squared plus A squared. And that's how you get it, if you did this. All right, I have that. Now the next thing I have to talk about, I'm contrasting these so you see this. One other thing, what happens is, as L gets very large, or the ratio of L over A, this is A gets very large. What happens to this? Take a look. This is at any point Z, but if you let Z equal 0 right at the center, let me do it this way. This is for h at any point on the z-axis, where z would be this way, and this is assumed the origin right here. So at any point z. So what happens is L over A goes to infinity, and I want h at z equals 0, right dead center here. What happens? When z is 0, what do you get? That's 0 and that's 0, right? That's 0, correct, class? Follow me what happens. If z is 0 and the ratio of L over A goes to infinity, then I have L over 2 minus a minus L over 2, or just L on top. You see that? And then I have L on the bottom, so L's gone. Do you agree, class? Now, if L's gone, what do you have? I have this minus this, and that's a minus. Sorry, that's a minus there. And when this comes out, that goes away. I get Ni over 2, and then this is going to be oh, wait a second, then it becomes a plus, sorry, not that. There, it's a plus. So now I have this, and when that's done, that's 2 comes out, so I have Ni over square root of L squared, or just L, and this is the answer for h at z equals 0. Right here. It's Ni over L. And that's h at the dead center of this. I'm going to tell you one thing. If you look at these two, they're almost identical if you make one stipulation. What's the total length if you straighten this thing out? How long would it be? 2 pi rho, right? Well, look at this. If you take Ni over the length, you get Ni over the length. They're the same exact form right there, okay? So really, if you want to know what the H field is at the center of a solenoid, just think of a toroid. Break it at some point and straighten it out. It's the same thing. Follow me on this, class? I think about that. It's easy for me to see that then, how the two are basically the same. One's just turned into a donut. Okay. Now, next thing we're going to do is magnetic forces. I posted some homework. Did it post, right? Okay, you all did it? No questions? Okay, good. I have your quizzes too, but I don't know if I have them here or upstairs. Let's look one look. I'll pass them back. Yeah, this is 30 through 10. Allie Brown. I'm sorry, I didn't get Alexander. Alexander. There you go. Ivan. Josh Tong. Regan. Brian Olson. Gaines. Andrew Mitchell. It's not it? Andrew Mitchell. Jared. Charles. Oh wait, no, Chris. What is it? Is it Charles? Sorry, I don't have my glasses. And you turn, yeah.
I was just looking at the solenoid one on the homework, and
Did you take the quiz?
No, I wasn't here Friday.
Okay. You have an excuse?
Well, I was sick at home. I can get it.
It's all right. We'll talk about a makeup after class.
Okay.
Okay. What we say?
I was looking at the solenoid problem, and at the end he has H equals Ni over 2H, but obviously the H's would cancel times. It doesn't cancel out the square root of Z plus.
Show me. No, that's the general formula, right?
Is it just?
That's not for an infinitely long one. See, that's this.
Okay, so this isn't okay.
This is the one I put up right on
Yeah.
the board. And the thing is it goes to infinity. What I wanted to show you is, if you get a very long, if the ratio of the length to the radius is getting large, then this H field and the center of both are the same. That's my point.
Okay, okay.
All right.
Because that would be okay. Cancel.
So with the forces, I wanted to do a couple of problems. And I got to talk about the torque too. Now, I showed you the thing about the two rails, right? Remember, currents in the same direction caused the wires to pull together. Currents in opposite directions cause them to repel. I'll add one more thing about this. When we did the railgun thing, we didn't know how, I didn't even think that the force could be so immense. When we discharge these capacitors, now we have very large currents, up to 400 kiloamps. They're only there for an instant. But we had wires separated by this far back, but we didn't have them tacked down. So currents in the same direction pull together in opposite. This is a differential. The capacitor is discharging. Positive charge causes current to flow this way, but there's a return current, right? And those things jumped apart. I mean, those things flew apart, and I wasn't expecting it. I didn't even think about it. So we had to pin everything down. You wouldn't believe the problems we had doing that. And that's when magnetic forces caused by currents became very real to me, and I got very, after that point, anytime I was dealing with large currents, I always calculated, try to get an estimate of the magnetic forces involved on nearby conductors and stuff like that, because it's really kind of alarming when you see wires jumping and arcs coming out of the wall socket and stuff like that. You really don't have a comfortable feeling because you don't know what's going to happen next. Anyway, that was an interesting time, I'll say that. So now I want to do the forces. And then, let me do the forces in this one. This was a homework problem, I believe. I have I going up, right? And this is a typical problem. Then I have something with a square here. And I'm going to call this I1 here. And I'll have a current flowing this way here, I2 here. Do you remember doing this one, class? I mean, for homework or not? Do you remember this one?
No.
Isn't this a homework problem? I thought it was. If you didn't do it, if you didn't do the homework, I'm not trying to force you to.
There wasn't no new homework.
What?
There wasn't no new homework.
It didn't post.
No, sorry.
It's more 14.
Yeah, it's only the one.
Well, there was supposed to be a new homework. I had it out. I thought I had it out at least.
I thought, yeah, that's kind
What?
I thought homework 14 was new.
Yeah, I didn't see homework 14 before Friday.
You didn't see homework 14 before Friday?
No.
It should have posted Friday.
Yeah,
And it
the
should have had this
most
one.
recent one was on the tours, is the last problem.
I don't know how I missed this one. This is the one I wanted to talk about because I had it in my own. All right, now, what I want is the total force. I want to figure out what the total force is on this loop. And this is a very good one. So how do you figure it out? How would you guys figure it out? I'm asking. We're supposed to have discussions in this kind of course, so here's a discussion. How would you do it? You're getting a test on Wednesday. This is a very likely candidate problem. How would you do it? Any ideas?
Find the current going down and the current going up.
Well, the current, we got the currents. I'm giving them to you. So we don't have to
Find the forces that are.
All right, so where do you want to start?
The magnetic force on the I1.
All right, but we need something even more fundamental than the magnetic force. What do we need? The B field, right? So we're going to say that at any radial distance rho, the B field, which way is the B field going here? Into the board or out of the board? Into the board, right? So I'm just going to indicate it this way. Why don't I give it a little coordinate system? So if that's rho, x, y, into the board would be h phi. So what was the B field going to be? If it's an infinite wire, assume that's infinite. Jared, you want to continue? You're right so far. What's the B field? Do you remember?
No.
All right, the B field is always going to be mu times the H field. You know what the H field is from an infinite line? People? Anyone? It's just like the D field from an E field from an infinite line charge, only you replace rho L with I, and you replace 1 over epsilon naught with mu naught. So B is always going to be proportional to I, that we know. It's always inversely proportional to the distance away if it's infinite rho. And the factor that's multiplying it is going to be 2 pi. Now that's the B field. I mean, that's the H field. I over 2 pi rho. But now I've got to multiply it by mu naught. And that would be the B field and would be in the A phi direction. So now I got the B field. My next job is to get the differential force, right? And what's the differential force? Anyone? Guys, you remember? This is from Friday's lecture.
Current times velocity times
Crossed.
speed.
IDL, remember it's crossed. It's IDL crossed into the B field. This is so important you put that cross product there. So now I've got basically 4 sides, and I'm going to do it this way. Call this 1, 2, 3, 4. So there are 4 sides, and we're going to take a look at the differential force, and I'm going to make an argument of symmetry to dismiss 2 of these. First, what would the differential force be here? I want the force on 1. What would it be? Differential force on 1. Well, IDL is in what direction? Now think about it. Right here. Z-axis. IDL is
AZ.
in the Z direction, so it would be just I2 in this case, right? I2 DZAZ, right? So make sure you put that down. So it's I2 DZAZ crossed into the B field, right? The B field is going to be the same no matter what. It's just the intensity here will be stronger than the intensity here because it falls off as 1 over rho. So I have times mu 0 I1 over 2 pi rho A phi. Now, let me go ahead and do this. So when we're done with this, what happens to a cross between AZ A phi is minus A rho, right? And here's how, an easy way to get it. Aren't these 2 currents, this current and this current, in the same direction? What did I tell you? They pull together, right? So it would be in this direction minus A rho. Therefore, I have mu 0 I1 I2 over 2 pi rho, and it's in the minus A rho direction. And that's the differential force on 1. If that's, and it's times dz. Now take a look at that for a second. How do I get the total force on the first member? If I get a differential, what do I do with it? Integrate it from where to where? Well, I didn't put a height. So what I'm going to do is make this a nice square, and it has height h, and it has width h. So what would the differential force be here when I integrate this from 0 to h? Because that's really what dz is going from some point to some point plus h, correct? You'll notice nothing in here depends on z. So it's really going to be, when I integrate dz, I get z, and I evaluate from h to 0, it's just times h. Do you agree? That means the force on member 1 would be equal to mu 0 I1 I2 over 2 pi. And now I've got to make a stipulation about this rho distance. I'm going to assume this is separated by a distance, and I'll call this A. 2 pi A, and it's in the minus A rho direction. Does everybody see that? Right?
What happened to H?
It disintegrated. H, thank you. It should have been there. My bad. That's a lousy H. All right, now, follow me on this. We could find the force on member 2, right? Now take a look at this. If we talk about the force, differential force on member 2, what would it be? it would be equal to I dl, or I1, I2, times, what would dl be here? Now think about this. I'm talking about this member. What would dl be?
dy.
Well, if it was xyz coordinates, it would be d rho, if it's cylindrical. So it's going to be I2 d rho a rho, right? Have to have that vector term, right? And that's crossed into mu 0 I1 over 2 pi rho a phi. And therefore, you're going to get a differential force on member 2 equal to mu 0 I1 I2 over 2 pi rho. And then what happens when I get rho crossed phi? I get, class? A rho crossed a phi is a z, right? Times dz. Now we can calculate this force. We would integrate this. We would say the total force F2 would be equal to the integral of mu 0 I1 I2 over 2 pi rho. And then we have dz az here. And where would the integration start and where would it stop? Here to here, right? Or from A to, you're right, A plus H. Do you agree with me, class? Now what's that gonna be? Well, that means F2 would be equal to mu 0 I1 I2 over 2 pi. And what's actually, this should be d rho. I think dz, it should be d rho here. Wait a second. IDL. No. It's in the AZ direction, but it is d rho. That's right. So it's AZ, but this is d rho here. I'm bad about that. So this is going to be the natural log of A plus H over A in the AZ direction. Y'all see this? This has got an AZ direction of the force, but it's a d rho integration, correct? So 1 over rho d rho, integrated d rho is natural log of rho. When you put the limits on it, you get this for F2. Hold that thought there. You all see what I'm doing, right? Now, so that force is upward. Take a look at this. F1, I've actually got the direction drawn on. F1 is pulling it this way. F2 is pulling it this way, right? Now I'm going to ask you something. You see how the current here is the same as the current here, except the direction is opposite, right? Wouldn't you guess the magnitude of the force on this member is the same as the magnitude of the force on that member? Magnitude. Agreed? It's the same current over the same length of wire in the same B field, except the opposite direction. So what happens to the force?
It's just inverse.
It's going to be down. So IDL, right? You take IDL, the current you want the force on, IDL crossed into B, force would be negative, but it would be the same exact magnitude. So I can say that F4 would be equal to minus F2. And what does that tell you to? What's the net effect of adding those two forces together? If they're same magnitude, opposite sign,
Cancel.
they cancel. So in other words, the forces on these two members are inconsequential in the final total force. They don't matter. Now the third one here, this would be F3. What's the differential force on F3? It would be what? I2, what is the, help me out here with the differential length times current. IDL, what is it?
I2 DC.
Minus dz, right?
Minus dz.
AZ, right? Minus dz, it's going down, right? That's crossed into mu 0 I1 over 2 pi rho, right? and this is in the A phi direction. And what happens when you do that cross? You get what? Well, it's going to be minus mu 0 I1 I2, right? AZ cross A phi minus A rho, right? Right, but there's a minus sign, so it's plus A rho over 2 pi rho times dz. Now, do y'all follow me what I've done here? Everybody? What happens when I get the total force and I integrate it? F3 is really going to be the integral of this and this from 0. Actually, it really is over a length of h. So it could be from 0 to h, 0 to h. And what happens? That's just going to be equal to mu 0 I1 I2 over 2 pi. Now, what is rho replaced with? Because I put it this.
A plus H.
That's right. A plus H, right? And then I also have to multiply this times H. And then it is in the A rho direction, positive A rho. Now note, this force is pulling it this way out, where F1 is pushing it that way. But those are the only two forces that are, when you sum, are going to be non-zero. And so when I take a look at the total force, F total on the loop, that's going to be equal to F1 plus F2 plus F3 plus F4. Only two of those forces add up to anything, and it really comes out to be equal to mu 0 I1 I2 times H over 2 pi, and it's equal to minus 1 over, where is it? This would be A actually. Rho would be A here. Minus 1 over A, right? And then it's going to be plus 1 over A plus H, A rho. Now, if you look at this for a second, the 1 over A is going to be a lot larger than the 1 over A plus H, right? And if you want to, you could get a common denominator, but this is a perfectly acceptable answer for the total force on that loop. And usually when I give a problem like this, I will give you, I'll say this is 1 meter, this is 2 meters, something like that, and I'll look for the final answer to be calculated right. Because oftentimes when I see I don't know why this happens on tests, kids will write this stuff in ways that are just bizarre to me. I couldn't tell if it was a mu naught or a y. I mean, my handwriting's bad, but some people I think intentionally try to almost make it understandable, hoping to get some partial credit. Please be very legible when you do these things on my exams. And second, be logical in the order. And the final answer, if I give you exact coordinates, do the calculations carefully and make sure the answer is in the box and put units on it. Because if it's a negative versus a positive direction, it means a big difference as well as the units, okay? So sign errors. Any questions about this one? This is a good problem. Yeah.
Can you explain one more time why F1 and F3 don't cancel?
Well, F1 has 1 over A, right? All this that I'm circling is the same in both, but it has a 1 over A dependence, right? Now over here, look at this. This is all the same in that one. But now the dependence of this is 1 over A plus H, right? Make A1, make H1. This would be like 1/2. That would be like 1. 1 over 1. Follow me? That's the reason. It's a push-pull relationship. And the way you always get the direction of force, if currents are going in opposite directions but parallel to each other, it's repulsion. If they're in the same directions, it's attraction. And it makes the problem a lot easier to see. Agreed? All right. Now, in homework 14, do you have it up there? I want to make sure, I'm thinking, how did this not publish? The problems, oh, that's okay. Can you go up to where the problems are that I gave you?
No, it's not.
Yeah. 417, all right, take a look at 424.
24. Oops.
A little higher.
4.2. Oh, right, 4.4.
Oh, sorry. Okay, I know.
Alright, you want me to scroll down?
Yeah, go, let me go up.
Okay.
Keep going. Okay. No, that one didn't post. Thought I had
I can look for it in the book or there's a.
No, it's all right. I wanted to make sure that we talked about this one, because this is a good problem. And I'll tell you one other thing too. What's easy to do is imagine different geometries here. You don't have to have a square. You could do something where it could be this. And this is a tougher integral one. You could have something like this. And you could have current this way. All right? Now in this member, it's pretty clear. It's really gonna be what? This current, call this I2 here. This member is just gonna be attraction, and it's gonna be mu times I1, I2, right? Times whatever this height is, h, right? Over 2 pi divided by 8. Now on this one, what happens? Well, that one's gonna have, if you think about it, it's IDL cross B, it's a force downward, right? And that one's gonna have the logarithmic variable, right? But what about this one? It's gonna have both. It's gonna have both a linear and a logarithmic term, because DL on this one, what is DL gonna be? Well, it's gonna have a D rho component, right? And it's gonna have a DZ component. Do you follow me on this? And it has to also be a unit vector. Well, I'm gonna tell you about this one for right now. This one is something that you always keep this in mind. Anytime you have a closed loop like this and you put an actual magnetic field caused by an infinite conductor, where the magnetic field does not vary in the z direction at all, there is never movement up or down to this thing. There is only movement this way or this way. You with me on this? And the way you actually calculate it, I can tell you for this one, you can forget about the dz component of the force. It's not going to affect it. What you have to find is the d rho component of the force, and then just integrate that one out. All right? And that one will end up being a linear multiplier. I can tell you that. Anyway, I don't think he has that one in the book, but a lot of times what professors do, there's another one that they do something. It's this, they make a circle, and they have current going this way, or I2 this way. And they'll want to know what the force is on that one. There you have to write the differential length, right? And then you have to go ahead and do the cross product to get the differential force and do the integral over the entire loop. But this is a tougher one too. Okay, class? If this is h and this is h in length, what would dl be? Now think about it, we're going this way. So first, the current would be I2, right? Y'all give me that? That's the current. If I want dl here, I know I'm going to have what? It's going to have an a rho component, right? And it also is going to have a minus az component, right? Now remember, for a unit, let me do this with a unit vector. I want a unit vector in this direction, I'll call it AL. If I want AL here, I know I'm going to have a proportional thing to deal with. And if that's h and that's h, this is 45 degrees. Do you agree with me there? Now, that means the slope of this, it's a minus 1 on 1 slope. Or AL, the unit vector, would be a rho minus az divided by the square root of 2. And the reason the square root of 2 comes in is because if you take these terms, square the coefficients in front and take the square root, it has to be 1 for a unit vector. Right? Everybody with me on this? So this would be AL, and when you get DL, it would be equal to, and then you would have D rho, A rho, minus dz az over the square root of 2, because it has to have that, anytime you're doing a differential link, there's a differential here, but there has to be a unit vector next to it. And it's either gonna be az, a rho, a phi, or a combination thereof. In this case, it's a combination. If it was 45 degrees. If it wasn't 45 degrees, I'm not trying to take too much time on this one, but I'll do it right here. You had this in calculus, but suppose I had something like this. Let's make this any angle theta, and I wanted a unit vector in this direction. Call that AL. So how would I get that unit vector? Well, think about this for a second. If I take a projection, let's say I've got a distance 1 here. If I take a projection on this axis, what is that distance? Well, it would be the cosine of theta, wouldn't it? Agreed? And if I take a projection on this axis, what would this be? This length? Sine theta. Now, that gives you all the information you need to know. If you want a unit vector, you can see that it's going to be positive rho, right? So it would be the cosine of theta, a rho, and minus the sine theta, a z. That's usually, I'm not sure how they teach that, but it's always has to do with a proportional slope, or the actual sloping effect, right? And the easy way to get that is with trig. And if you look at that right there, just take the coefficients, take this coefficient squared, cosine squared, this coefficient squared, sine squared, add them up, sine squared and cosine squared is 1, square root of 1 is 1, the unit vector has a value of 1, right? But you would still have to have cosine theta a rho. For the differential length, it would be equal to d rho cosine theta a rho, and then it would be minus dz sine theta az. You have to make sure you put the associated differentials on it. Follow me, class? This, I know it's a little beyond the scope right now, but you have to get an appreciation for this kind of stuff. Because a lot of times, in the upper level courses, they're assuming you're familiar with this, very familiar. And if you're not exposed to it, it'll strike you and scare you, some of the stuff. But you've had that back in the day calculus, didn't you, right? You had all that? All right. Next. We've got a test. I can carry on here, but do you have questions about the examination, about any problems prior to? I mean, anything, because the test is comprehensive, it includes everything up through this lecture. If you have nothing, I'm gonna forego torque and I'm gonna cover inductance, but magnetic energy. But do you have any questions at all? By the way, you're not responsible for any new material today that I present. I put that problem up, I think, on Friday, didn't I? I sketched that, something like that up there. I had it in my notes. Do y'all remember that at all? Do you remember the force problems where we had 2 wires parallel? Yeah. Well, those kind of problems are legitimate for the examination coming up, all right? Because I gave them to you, and I gave you homework, I think, with some of those things, right? But I'm not going to ask you anything about inductance or any other material that's new. Any questions at all? Usually, students by this time have thought about the examination and they've done a fair amount of review. No questions, not even from you. No?
I don't have like a problem, but can we do one where you've got like ER and then E1? Or,
Epsilon, you mean?
well, no, E1 and E2, like where you have the vectors.
You mean adding vectors? I'm not sure what you mean.
Dielectrics, probably.
Are you talking about dielectrics?
I think so.
Take a moment to figure out what exactly you want to ask me. Anything else? Remember, it's all inclusive. It goes from transmission lines, so you know you're going to get a transmission line problem. You know it could be transmission lines, then you're going to get standing wave ratios in there, right? Power, huh?
Impedance matching?
Sure. we can do one. Do you have one in mind? I mean, I can whip one up in a second, but it's been a while since we've touched on transmission lines, but Smith chart, by the way, why don't you guys, if you want to, bring a couple of Smith charts, make sure you have a compass and straight edge, and make sure you bring a sharp pencil, or, I mean, a sharp, pencil.
How many questions is it?
Oh, I always get that. This is kind of it's going to have probably 4 or 5 pieces of paper, each with a stated problem, but there'll be multiple parts I'll ask you. So when questions, it's hard to say. You're going to get at least 4 or 5 major themes, and there'll be multiple things. Like with a Smith chart, I'm going to ask for what? How long's the stub? I'm going to ask for probably the standing wave ratio or something like that before, after. I can ask you a lot, but all these impedance matching problems have several parts to them. And I always want you to do one thing for me on the Smith chart that you turn in. Indicate the first point you came in with a 1. That's where you start. Then 2 where you go to, 3, and then 4. I mean, show me the logical order that you do things. Because a lot of times, I can't know what you do. And sometimes that's intentional because you don't know what you're doing. Go ahead.
Can I read the problem?
Yeah. Which one is it for everybody?
2.38.
2.38.
A load impedance ZL equals 200 plus J 160 ohms is to be matched to a 100 ohm line using a shorted stub,
Shorted stub, yeah.
Shorted shunt stub to
Oh, shunt, yeah. So it's in shunt and it's a short, okay.
find a solution that minimizes the length of the shortened stub.
Okay. So, y'all have your Smith charts at all? I'm gonna just try to sketch the Smith chart. I do this routinely. I'm not saying I'm not good at it, but it's a good place to try to estimate what it looks like, something like that. And I usually call it the equator, but it's a horizontal line through the center. Then I indicate where the center is, and I draw the 1 circle. This is R1, right there. And now I start doing this problem. So, if you remember these things, when you're doing impedance matching, the first thing is, let me sketch out what we're looking at here. We're looking at a load here, some ZL that's 200 plus J 160. And it's right now tied on to a characteristic impedance of 100 here. And they're looking at the distance, L through, and L stub, or however it calls it. He's looking for these 2 distances. But what his stipulation is he wants the stub length to be minimum, right? Doesn't he say that? So he wants this minimized. Minimum length. Here. That's his goal. All right, when you do a Smith chart problem, this is in shunt, so we're going to be working in the Y domain, the admittance domain, not the impedance domain. You agree, class? Remember, if we add admittances, they're like resistors in series, or they're impedances in series, correct? Y'all remember this? So let's start this problem out. First thing we do is going to find small ZL. And that takes ZL, big ZL, divided by Z naught, the characteristic impedance. In that case, it's what? 2 plus J 1.6. Do you all agree with me there? So you find that point, and I know about where it is, because I know it's going to be, there's going to be a 2 circle here. The real part's 2, right? So that's R equal 2. And the imaginary part is 1.6. Well, I know straight up here is J1, so 1.6 is about here, I think. So you're going to have one of these arcs coming through here, and that means this point should be 0.1, and that would be 2 plus J 1.6. Can you all see that on your Smith chart? First, find that point. See, I need glasses when I do these things. Sometimes magnifying glasses. You all see it? And you have a compass? How many people have compasses? You've got one. Wow, you guys are really prepared. You don't have this? I'm shocked.
I haven't had a compass since like elementary school.
You have them for these problems though, right?
No?
Well, just a tip, buddy. I think you need one,
Okay.
because for the exam. All right. I mean, really, how hard are they to get? You go to any bookstore, they have, right?
I have an extra one. It came in a pack of.
That's darn nice of you.
Hold on.
I can only find mine when it stabs my hand.
What's that?
I can only ever find mine when it stabs my hand.
Look, are we here to?
Yeah.
Now, Duke, I always recommend you do this. Just get a straight edge and draw lines right from the center of the circle through there, out to the edge, and through the other way, all right? I mean, something like that. Follow me? Just take it all the way through. Are you with me? Now, the next thing you have to do is locate this point. And this point is gonna be on the conjugate. If this is ZL, which it is, this is ZL, this point, same distance away, but at the conjugate point here will be YL. It's 1 over ZL. So if you wanna know what the value is, just take ZL in your calculator, which is 2 plus J 1.6, and take 1 over it. But it's probably just as easy to put a straight line through here and mark it there. And YL is what? It's going to be, I can't do that math in my head. 1 over 2 plus J 1.6 is what? Go to calculator. You can't, never mind, you just, is there any way you can prop that up so you don't have to hold it?
I have to like move it around a lot.
All right. Well, I appreciate you doing that.
0.30 minus 0.24.
0.30?
Yeah.
0.30
Mhm.
minus J what?
Minus J 0.244.
.244, right?
Yep.
All right, so that's your second point. And what I'd like to see in the test is a 1 here with a circle, then a 2 here, because now I'm there, right? And next thing you probably should do is take your compass and go ahead and make this circle right there. Remember, the circle, take your compass point and stick it right in the center of that Smith chart where it's just 0, 0. And then go out to the point and then draw a circle. With me, class?
Draw a circle.
Yeah, because this is the point, these are all possible values of impedance that will appear on that line as you move. If you cut the line here, or here, or here, you get either the impedance or admittance on that line before we do any stuff to it. Agree? Now, I have to talk about the stub for a second, because this is a minimization problem. It could be a maximization problem too. If you have a stub like this that's shorted, what is the Z load of the stub if it's short? How many ohms? 0 ohms, right? Therefore, what is Y load of the stub if it's a short? Infinity, 1 over ZL, or it's infinite ohms. Now, this is important. So, when we do impedance matching for the stub, we start at a point where it is infinity, right? Right, this is the point. This would be infinity, this would be 0. I think we all know that, right? You would start here if it's short. If it was open circuit, you would start here. Remember, I'm moving towards the generator if I'm here, so I'm moving this way, or I'm really going in this direction as I get further from that stub, right? You all see this? Now what values are appearing here? They're minus J values. Do you follow me on that? Right? They're minus J something, minus J. From right here, minus J 100, minus J 50, minus J 40, and so forth, right? correct class? So I know if I want this to be used for impedance matching and it's minus J, then I want to impedance match something where I got a plus J to get rid of. It would shorten that, right? Otherwise, if I had a plus J that I have to get rid of, then I'd have to go all the way to this point before I get positive values of J on the stub. Agreed, class? So let's do the matching. I've got YL is 0.3 minus J 0.224, and I need a mile mark here. Can you give me what this is in wavelengths towards generator?
0.459.
Is that right?
Mhm.
All right, now 0.5 is this point. So it's close. Now how far do I have to move? Now follow me. On this trajectory, I have to move to this point. That's the first point I encounter. But I could also do what? I could also have a point here. Both of these points, this one would have 1 plus J something, call it JX. And this point would have 1 minus JX. X would be the same. We're looking for the point where on this trajectory, we hit either a +1 plus JX or 1 minus JX, correct class? Now remember, we're adding the stub's impedance onto it, and we want the stub to be a minimal length. So if we start just incrementally increasing the length of that stub, we're getting negative values of J, right? So we want to make sure that we get the one that has the positive 1 plus J that. Follow me, class? And where does that value here, where the circle intersects the one circle? What is first the value?
It's like roughly 1.3, a little bit.
It's J 1.3?
Right?
Yeah.
Yeah, like a little bit over 1.3, just like 1.32.
1.32, all right. About that,
Yeah.
guys?
Close.
All right, now, and that would be your, you could call these 3, 4 right here, but that would be your third point right here. Right? Now, you have to do this. You have to take your straight edge and take it and go from the center of the circle and draw a line right through that point. And then find the mile marker here. This is 0.459 lambda wavelengths towards generator. What's this point? I need the,
Towards,
what is it?
which point do you need?
Well, see, when I take the straight line and I go through 1 plus J 1.32, the point where it intersects that,
Mhm.
and take it out there, I need this intersection, wavelengths towards generator, the outer
The
part.
generator is roughly like 0.17.
0.17? So 0.17 wavelengths towards generator. I always put wavelengths towards generator or wavelengths towards load if I'm doing this stuff in a serious way, because you can forget which way you're going. Now, what's my total length then I have to move before I patch the stub? This L through would be what? I'll let me do it here. I'm just calling it through. That would be, you take the point where you're going to, so it's 0.17, and you subtract the point which you came from, 0.459, correct class? Now we know it's in lambda. And then what do? What is that gonna be? What is it?
Minus 0.289.
Lambda. And what do I have to do because it's negative? No? Add a half. So you add a half. Now what do you get?
0.211.
0.211 lambda. So L through here is 0.211 lambda. We're almost done. Anybody want to help me on the final step? How to calculate L stub? Length of the stub, what do I need to do? Well, what do I have to get rid of? J 1.32, right? So this is J infinity. Now I come down here, I get minus J, and I'm looking on that line until I hit probably about here. Minus J 1.32. Can you see it? That's going to be on the rim there, on the very rim. You're looking at where the perpendicular intersection occurs of these trajectories right here, like where it comes in perpendicular there, and you're going to see down here a minus J 1.32. You all see that?
Yeah.
Please make sure you look at it right now. Do you have a Smith? Do you need a Smith chart?
Yeah, I didn't bring one.
Anybody have a spare Smith chart? It helps to look on these things. Are you with me? Now what do I need to do? I mean, first, once I identify that point, what's my final task? I need the length, right? So what do? I start here, right? And that's 0.25 lambda, right? And I find how far I am from there in terms of taking a straight line. You gotta do this with a straight edge from here straight through there, and then look at the distance marker in the outer part. Wavelengths towards generator is what? Just tell me what it is.
It's like 0.328.
0.328 lambda. Now that's not the length I need to go. What do I need to actually go? My L stub, I mean, the length of the line would be what? That 0.328 minus 0.25, right? Lambda, correct, class? So that's what, point 0.078, right? 0.078 lambda. Does anything trouble you about that?
Okay, so are we looking for where the 1.32 is on the outside or where it intersects the articles?
You're looking at, here, let me show you actually. Passes. You're looking for where the intersection is on, right, on this rim where it's minus J 1.32.
So you're just looking for where that value is on the outer ring, not where.
No,
it
I mean,
intersects.
that's gonna be the intersection, then you draw a straight line through it.
So like,
See these point 4, 3, so minus J 1.32 is, yeah, right about
so
here.
we're not looking for where it's intersects.
No, this is on the edge, because this is the impedance, there's no real part.
Right.
When you take ZL as 0, 1 over, I mean, it's J, actually, that 1 over that is infinity, and that's where you start, but it's J right here. So if I'm going down there, all these are J something, there's no real part. Now you're going down, if there was a real part, it would be in here. So you're going right on the edge in here, 1.32, about there. You're just gonna draw a straight line through there, and then on the outer marker, I'm seeing 0.35 something on mine.
The one over here.
What did you give me?
Can't remember.
No, it ain't 0.32. Can you give me the right value?
Is it not 0.32?
No, look, I don't know what you did, unless the Smith chart's wrong. But, give me that. 1.32, see, you're right here, and you're looking for 1.32, it's about there, right?
Oh, okay, I did it from the point.
No,
Okay.
you don't move, you're moving right on the rim, you're not moving on the circle that you drew earlier. This has got, this point right here has to be right on the rim. It's not here. All right, when we're doing impedance matching, we start here, we have 0, 1 over that is infinity, we're right here. We have no portion inside here, and now we're moving on the rim.
All right, then it's 0.354.
Okay, that makes my heart feel a little better. This is 0.354. So what would the length be? About 0.14, right? Isn't that about 0.14?
104.
1.104 lambda, just barely what inside. Now here's the deal in the real world. This has to be at least 1/10 of a wavelength. That's right at the border, all right? The 0.07 lambda was too short to really use impedance matching techniques. You would have to do impedance matching, you would have to go around the loop again, a full half wavelength, before it would be considered a true transmission line. In other words, the stub would have to have another half wavelength added on. Follow me, class? Are we there? It's not a bad problem, right? Ask it, go ahead.
why did you find, I was with it all the way until you got to the 0.17 wavelengths till generator?
Well, we have to get to the point where I have 1 plus J 1.32, right?
Yeah.
Or 1 minus J. Well, 1 plus J 1.32, I gotta find how far I have to move, right? So here's where I started, 0.459, I have to move, throw a straight line through there, 0.17, right? So I take this value minus that value, it turns out negative, so I add a half wavelength to that, and that's this distance. It's really, the distance I'm moving is from here to here. That's the L through.
So why did we find the negative one on the bottom?
Because we're trying to eliminate when we're in the admittance domain, right?
Yes.
So if I have an admittance looking this way of 1 plus J 1.32 ohms, right?
Yeah.
And I'm putting something in parallel with it. That means this stub has to have minus J 1.32 ohms to cancel that, so we have 1.
Okay.
That's the idea. We want to be, at the end of the day, we want the normalized impedance after you add the stub to be 1. Fair enough?
Yeah.
Now, I gotta ask you one more question here. Before the actual stub was added, what was the standing wave ratio? Or voltage standing wave ratio? Do you remember? What's the equivalent? Huh?
3.5.
Ah, good. But I mean, the formula you would use is what? 1 plus the magnitude of the reflection coefficient of the load over 1 minus the magnitude of the reflection coefficient of the load, right? It's going to be at least 1 or greater than 1, and it's always positive. What I see all the time is people using 1 plus gamma L and 1 minus gamma L. That works great if gamma L is a positive value. But if gamma L is a negative value or it has imaginary components, it's completely wrong. You gotta take the magnitude of gamma L. And by the way, what is gamma L, the reflection coefficient? It's ZL minus Z naught over ZL plus Z naught. Agreed, class? Something else I'm going to add here. On the examination, I will give you the classic formula Z in is equal to Z naught times ZL plus JZ naught times the tangent of beta L over Z naught plus JZL tangent of beta L. I will give you that formula. Just because they mess it up so many times. I'm going to tell you something else though. This calculation, even if you have that written, because I'm giving you the formula, if you don't know how to calculate it right, and you come up with the wrong answer, it's wrong. Now we did this, I had this discussion with this class before. I had warned you how oftentimes students mess that up, and then we proved, when we did it in class, how many different answers we got. Do y'all remember this?
Yeah.
So be very careful when you're doing this. If I was you, I would probably program in my calculator, literally, that's something where I could just enter in beta L in radians. I could enter in ZL in ohms and Z naught in ohms, and voila, out comes the answer. Because man, this one they mess up, people mess this thing up more than any other thing I can think of up to this point in EMAG 1. Okay. Other questions? Yeah.
Let me just read it for you.
Yeah.
All right.
Is it a problem?
Yes.
Well, let me clear the board and we'll get it.
So, we start at 1.5, so that's what you start. End up 0.14. Yeah, so that's where the outer round meets with the negative 1.3 whatever.
It's minus or plus.
Go ahead.
Suppose coaxial capacitor with an inner radius of 1 centimeter, an outer radius of 2 centimeters, and a length of 1 meter. It is constructed with 2 different dielectrics.
Half, like this and this?
E-
Or is it,
yes.
okay, I think we did this one. This would be like epsilon 1, and this would be epsilon 2, or epsilon relative 1, epsilon relative 2? Do
Yes.
you remember this one, class? How did I tell you to do it? You might have missed that day. How did you do it? First, you find the value of the capacitor is if the whole thing was filled with just epsilon, right? And that capacitance would be what? It would be 2 pi epsilon, right?
Epsilon R.
Yeah, well, all right, epsilon r over natural log of b over a times the length L, right? And then I told you how to do it before. I'd say if I wanted the total capacitance between the inner and outer, I could say it's 1/2 the value of 2 pi epsilon relative 1 epsilon naught over the natural log of b over a times L, right? So it's got 1/2 as if the whole thing was filled with epsilon relative 1 plus 1/2 times 2 pi epsilon relative 2 epsilon naught over the natural log of b over a times L. And what I'm doing here is I'm saying, I know if the whole thing was filled with epsilon relative 1, right, it would have this capacitance. But only half of it has that. And I made the statement they're in parallel too, right? So because of that, I multiplied by 1/2. That's the fraction of the area of the plates that have epsilon relative 1 between them. Then I added to it 1/2 times 2 pi epsilon relative epsilon naught over the log of b over a times L. There, that's the capacitance as if the whole thing was filled, the capacitor with just epsilon relative 2. And because the proportional area was 1/2, I put a 1/2 there, right? Now, if the proportional area was 3/4 was epsilon relative 1, then 3/4 would go here, and 1/4 would go here, and so forth. You can do the permutation. I could make it 3 different dielectrics, all equally with an equal amount of area, right? Plate area. And then it would be 1/3, 1/3, 1/3 times the natural log. I mean, as if the whole thing was filled with the with only one dielectric, right? All right, I'm throwing that one out. That's not a bad problem. Anything else? Think of that with resistance too, right? It would be resistance in parallel, right? Anything else? All right.
Can we do 362?
Gross is gonna throw me out. I'll do it upstairs if you wanna come down. If anybody wants more problems, come on up to my office, because Charlie Gross is gonna come in here. He's gonna